So, we will continue with storage and as I was mentioning in the last class that we optimize the size of the storage. We take say supply cost, we write it as F s, where F is a function of supply rate. So, supply cost is cost of supply is function of supply rate, and basically we must maintain this condition that total supply over the time period, because it is a periodic 24-hourly you said, must be equals to total demand, otherwise either it will have overflow or you will not be meeting the demand. At any point the difference between the cumulative supply and cumulative demand, that would give you the kind of a storage, right. So, this is because this is supply is more than, now in this case supply is more than the demand up to a time theta. I mean this should be some t, small t maybe up to time t. So, y is time t, or this should be written as dt, whatever it is. So, it can be written like this: y theta is equals to 0 to theta s t dt minus 0 to theta d t dt, something like this, 0 to, yeah. So, you write it. So, this is the difference. So, this difference is what gets accumulated, and if this is bigger and this is smaller, in other words one can write it in form of difference. If this is bigger, this is smaller, in that case you must already store it to maintain the requirement of demand. So, this y theta is basically the storage, y theta is basically the storage, y theta is basically the storage. So, if I differentiate this with respect to theta, where it is maximum, say y is maximum or minimum, minimum is negative side, s theta will be equals to d theta. So, the maximum comes where this s theta is equals to d theta, s theta is equals to d theta. So, that's from that we can actually find it out actually. Let us see how we do it. I think last class we were talking about this. So, one can actually plot this once. For example, this is the time period and my demand requirements are something like this. Now, as I said that cumulative demand must be equals to, over the time period, cumulative demand must be equals to cumulative supply, otherwise I will have overflow and storage, etc., etc. So, as we said, or I will not be satisfying the demand. So, this has to be periodic over the time period, that is 24 hours in our case. This must be, condition must be satisfied. Now, if I want to find out the minimum supply rate which I require to satisfy this demand profile, which is given by this, and let us say we keep it constant. Usually supply rate we keep it constant. Why? Because it is difficult to vary it with time, which it means that you have a controller and feedback system, and depending upon what is the demand you try to, which is not easy. I mean possibly with very good control system you can do, one can do it today, but generally this is not done. The simplest thing is to have a constant supply rate, constant supply rate. So, minimum constant supply rate, let us say if is n, this must be equals to S min into T, because then this is constant S min and this is T. So, if you integrate it you get S min into T. So, minimum supply rate is simply the area under the demand curve divided by T. In other words, it is nothing but the average, it is nothing but the average, So, this S min would be given by 1 by T 0 to T, that is what it should be. In other words, this is nothing but is this height, average basically. So, if you have sum total of this area under this curve divided by the base, this is what it is. So, this rectangular area, you know, so this is the minimum constant rate. And if I plot it in the cumulative form, that is, this is my time, this is my time, and this is the, you know, cumulative, this term, cumulative demand or cumulative supply, then cumulative demand would look something like this, right. So, because this is a summation of this area, so up to this is this area, total area. Similarly, now it starts reducing, the slope would change. So, this is cumulative demand would be written in this manner. Now, this one, when you have a constant supply rate, cumulative supply would be simply a straight line. Cumulative supply will simply be a straight line, right. Cumulative supply will simply be a straight line. So, they must match here, because after the cycle, after the period, the total cumulative demand must be equals to total cumulative supply. So, all you can do is you can even plot this cumulative demand and just go to the last point, join them, the slope of this line gives you the supply rate, slope of this line gives you supply rate. Now, if you look at it, what will happen at this point of time, let us say we are somewhere here, right, and I have got a supply rate which is higher. So, it will go on storing, because supply rate is higher than the demand. So, you know, it will go on storing. Let us say this is my hot water case and this white color is the hot water. So, you know, this is the situation from previous scenario. Now, it will go on storing till this point of time. After that, demand has exceeded. So, it will go on consuming them, you know, it will go on consuming, and the consumption will become again possibly maximum, you know, it will whenever it goes down below this line, it actually demand increases. So, storage reduces, and again storage, additional storage, and then again there is a, you know, the supply rate is more, so storage increases actually here. So, this is how it progresses. This diagram and this diagram is same. So, we want to find out what is the capacity of the storage I require. Now, capacity of the storage will be maximum of these differences, because this height gives me what is the difference between cumulative supply and demand. So, whatever is, you know, this plus this, maximum of this and this is what I will require as a storage. So, storage would be given by maximum of y or plus absolute value of y minimum, absolute value of, you know. So, this differences would give me the storages. Yeah.
So, in that third rectangular storage thing,
this one.
Yeah, this one. So, here also the demand is more than the supply, right?
Right. But what has happened is demand rate reduces slightly. So, it stored a little bit.
But still the supply is less than.
Yeah, supply. That's why you have got still lot of, you know. So, that's it's accumulating actually. It's accumulating. I mean, not accumulating. It's consuming. Sorry, accumulation is white color. Yeah. So, the accumulation. So, here the maximum accumulation has actually occurred here from here, because this is supply is higher. Then here also supply is higher.
Accumulation is the white thing.
Okay. Accumulation is Y and the consumption is the black. White means hot water, the hatched or the darker one is cold water. So, you are heating it, you know, so hot water is withdrawn, the water supply, I mean water supply is there, but at the same time heating is also there. So, you know, your heater is operating. So, when that's how it is basically. So, hot water as this is all hot water and this cold water and there is a heating period. So, that is how it is. Now, this therefore, these are the cumulative, if you look at it at this point, as I said, when d theta is equals to s theta, that is where you get, you know, the difference is maximum y, either get y theta max or mean, whatever it is. So, this is when this is equals to this. So, when they are equal, this difference is maximum. Again you will have somewhere they will be equal. So, you will find there is a difference, and whenever they are equal you find the difference is maximum or negative side maximum. So, the storage is given as a sum total of maximum of these two, because this is in the cycle, whichever is higher, that is what it is, plus this one. So, total storage is sum total of this maximum and minimum, because you need that you need that whenever this is higher, that means you got to store it, and these are the cases where you have to draw it. You will consume all the storage, whatever you have stored, the consumption will finish there. Then you must have adequate available, so that you can withdraw more. So, that is why the maximum of these two. So, that is how you actually find out. So, what I can do? I can actually see that these gaps becomes minimal. How can I do it? Supposing I instead of this, what I do is I do it, I stop it here and then go, I stop it here, go possibly like this, try to come, this is my demand is anyway finished. So, initially I start at a rate like this, then stop, fixed rate has to be fixed. I cannot change the slope of this line. So, maybe I go something like this, stop, then again start from somewhere there, go at the same slope and so on. So, this is what is shown in the next diagram. What I have done is, now I have increased my slope, this value has increased, this value has increased, but not I am trying to match it as close as possible. So, operational the periods, I do not have continuous now. What I do is I supply sometime here, sometime there, and then of course, I might supply something like this, such that the maximum of these values is and minimum or maximum of this negative values, this is practically 0, very small. So, my storage actually would get reduced down, because earlier it was sum total of this plus this, now it is only this value. So, I can match it in such a manner with intermediate supply, so that my storage reduces down. But what I am doing, I am increasing the slope, that means my supply rate is increasing. So, when supply rate is increasing, that means my cost of supply will increase, either the heater capacity, the pump, everything, something will increase actually, all right. And I can do it further. So, if I do it further, it would be something like this, here the storage is reduced significantly. I have operating schedule, I have fixed it in such a manner that this storage has reduced, but this supply rate has increased, the slope has increased, right, slope has increased. Okay. So, this slope has increased, all right. So, I can have several supply rates and several storages corresponding to a demand profile. The demand profile is same. So, I will have a series of supply rate and storage which will satisfy the demand profile, right, which will satisfy the demand profile. So, what I can do is, the supply demand built up one over other results in storage requirement, as we have stated. As the built up climbs down from peak storage requirements, built up climbs down from a peak storage, requirements reduces till there is a change in sense of built up, either the positive sense of built up or withdrawal, negative sense of built up. So, capacity therefore is maximum delta t into delta t I, if I am taking delta t time interval, minus S t if it is constant, and minimum plus minimum of this one. So, as I said, so maximum of A 1 A 2 or Y 1 Y 2 and maximum of B 1 B 2, that is what I was saying. Maximum of this you call it A 1 A 2 or B 1 B 2, B 1 B 2 is here. So, maximum of or Y 1 Y 2 etc., I can call it also. I am now differentiating them as A 1 A 2 B 1 B 2, where A 1 is the difference between cumulative supply and demand, right, and positive, and here the same negative, that is now so whichever is maximum, take absolute value of them and sum them up. So, for intermittent supply, same procedure will remain valid, except that supply is some period now is 0. So, for higher supply rate, satisfying the same demand profile, one can obtain, this is the constant one, simply the time period is the time when there will be no supply. So, cumulative demand and cumulative supply shall match at the end, and this is that this is the period. So, S 1 is the supply rate. So, the one can, that formula already I have told you. Now, you can find out the total cost, because you have now, I can draw it like this, tabular form, my demand profile is fixed. So, supply rate and storage. Now, if I call it, I think I am using a nomenclature, C is the storage and S is a. So, I will have set of S1, C1, S2, C2, S3, C3 etc. for same demand profile. For a given demand profile, I will have set of. Now, this would be simply, as I said, average, the minimum. This is the d theta 0 to dt 0 to t 1 over t, that is equals to the first one S1 that is equals to S1. S2 would be now higher supply rate, but this will go down. S3 will be still higher, this will go down and so on. So, for the same demand profile, I will have set of these values. Therefore, total cost I can find out. Total cost will be cost of the supply and cost of the storage. So, I can so since this one I know, I can find it out. So, that is total cost is, if I call it cost of storage as CC, total cost, and cost of supply is S, CS, this total cost I should be find out. Now, supposing I know the unit cost of unit per unit, if I know per unit, then simply multiply this and you can find out. So, that is what we can do. Let us see how it goes. So, S and C would, as S increases, C would reduce. So, cost of supply, cost of storage, cost unit supply, cost of rate of supply, rate of storage. So, if a total cost has a linear relationship, okay. Now, this cost, total cost, I can, for example, if I know the value of supply and it is linearly related, for example, if T C is simply C C C S multiplied by S plus C C multiplied by C, right, then in that case it is a linear relationship. I can choose a value of S, and keep this value constant, then I can find out C, right. Choose a value of S and choose a value of, choose this value is constant, corresponding C value I can find out. See, the thing is that I can now plot for different T C values, choose one T C 1. Now, this cost is known to me, this cost is known to me. For any given S, I can find out the corresponding C which will satisfy T C 1. Similarly, I can have T C 2. So, I can go on finding out several curves, I can go on finding out several curves, several T C lines, I can find out several T C line, right. Now, there will be line, but if it was function of this kind, that it is S square or something like that, then it will be kind of nonlinear parabolic curve. So, one can actually obtain something like this. X is, let us say, supply, or what I am calling as S, and this is my C. So, for each X and I can find out the cost. So, this is the total cost I can find out, and I can plot this cost versus. So, this is basically constant T C value, constant total cost value, and combination of C and S. So, this is S, this is C. So, this C and S satisfy. So, this is a curvature, this is showing it is not, it is linear, not linear, but had it been linear, it would have been something like this. For given S value, I have a T C 1 value, T C 2 value which is smaller, and T C 3 value etc. smaller. So, I can have set of curves for different T C values. For different T C cost, total cost values, I will have set of curves, right. Now, this will go on increasing with cost, T C curves will go on increasing with this cost, and I already had a cost, demand supply, because I said I had S1, C1, S2, C2, S3, C3 which satisfy my demands. So, I can plot them. This would look like this, typically this will look like this, and cost curve will increase in this manner, cost curve will increase in this manner, cost curve will increase in this manner. As my cost increases, TC value, TC curves, which could be straight line also, wherever they touch, because this is the profile, like I had S1, I had S1, S2, S3, etc., etc. Now, this curve is what we call iso demand curve. Demand remains constant, iso demand curve, and iso demand for a given demand profile. These are the combination of S and C. So, this is S1, C1, S2, C2, S3, C3. So, this is iso demand curve, right. Demand remains constant, for that I will have set of S3, S1, C1, etc., etc. And then I just think in terms of the cost, I think in terms of cost, think in terms of the cost, right. These are the iso cost curves, iso cost curves, right. These are the iso cost curves. So, cost increases TC1, TC2, because if it is simply, as I said, TC is a function of some unit cost multiplied by S, could be S square or linear if it is then, and Cc into Cs into S and Cc into C if it is linear. If it is parabolic or something, then because it may not be linearly increasing with supply rate, it might vary depending upon, because it will depend upon the pipe sizing, motor size may be, supply rate you want to increase, motor size, pipe sizing has to increase, storage means total storage capacity has to increase. So, they may be linear or may not be linear. So, somewhere this will touch, as you go on increasing the cost, somewhere it will touch, and that is the optimal point, that is the optimal point for us, this is the minimum. So, this point somewhere it will touch. So, this is the least cost, this side is your, so this side is your S, this side is your C, somewhere this will touch, and that is the optimal point, because that's this curve satisfies the demand and supply, and this is the cost curve, minimum cost curve, because any further cost means it will increase in this manner. So, this one can find out. In fact, one can simply formulate this as an optimization problem, right. But then this you can formulate as an optimization problem, because then you have to know the relationship between supply rate, right, relationship between supply rate, I mean explicitly know the relationship between supply rate and the cost, right. Also explicitly know the relationship between cost and storage per unit cost and storage, that you have to know explicitly, and you have to know the relationship between the supply and cost satisfying the given demand profile, relationship between. So, this relationship between this should be known. So, once these are known, then you can actually formulate this as an optimization problem, and you can optimize this, right. So, you can do just simply do an optimization. For example, you can minimize the TC if it is a function of S and function of C, function of S and C, if it is a function of S and C, you can minimize this, but then these values you must know explicitly, and relationship between C and S or constraints, it could be in the form of constraints that S and C should be related in such manner that S is some a function of f1 dash of S is equals to f double dash of C, because there is a relationship between f and C exists, which will satisfy the given demand. So, if explicitly mathematically these are known, you can actually arrive at you can do that optimization, but graphically this can be done in this manner. So, that is how we determine. Let us see as an example problem, simple example problem. So, let us say my supply rate is this is my time 1, 2, 3, 4 up to 24 hours. So, hourly demand is known to me. So, it is 180, 130 etc., etc. This is known to me for whatever unit it could be. It could be if it is hot water supply, or hot water supply cannot be like that, maybe cold water supply or something whose rate is known to me in some unit. I want to find out the optimal storage and best supply rate. So, first thing is you accumulate this sum total of all this demand, because it is 1 hour. So, 180 into 1 etcetera, etcetera. So, you get 2180 units. So, minimum supply rate would be this divided by 24, because that is the constant supply rate and it has to be minimum. Minimum constant supply rate would be simply 2180 divided by 24, 2180 divided by 24. Now, you can find out the difference between supply and demand. Cumulative demand minus supply you can find out. For example, this was the cumulative demand is 180. Next hour it would be 180 plus 130 cumulative. So, which will make it 310, next will be 310, and S into T 90 is the supply rate. So, first one is or 89.16 etcetera, second hour it will be double of that, because it is constant we are talking about. So, ST is 90, 181 etcetera. So, demand difference I am finding out, 180 minus 90 is this. So, this is the difference. Now, difference takes positive values, then negative values as well. Find out the maximum positive value and maximum negative value. Absolute value of that negative value will give me the storage capacity. Absolute, or you can plot it in this manner also. So, this is how it can give us. You can actually, so if you plot it, the the same one curve, just I plotted this values and these values, they would appear like this, they would appear like this, finally they would match, and the gap, maximum gap will be here somewhere and here somewhere. So, therefore, you can actually calculate this out, and this would turn out to be, this is okay, and you want to improve this, all right. So, you can find out actually the storage capacity, which comes out to be sum total if you take it 334, because the maximum of positive is I think 196, and minimum value, negative value, maximum negative value is 128. So, 196 plus 128, something like this. Just see, if you see the maximum value is 128, 167, 196.6, and that is it. There is a negative value is coming as 56, 137, sorry, 137. So, yeah, that is right, 334 point something, that is how it comes. So, that is the storage capacity I need, and my supply rate is constant here. Now, what I can do is I plotted this, I can do the same thing, change the supply rate in such a manner that it matches most of it, so that my storage just reduces down, but then I may stop, do it intermittently, may not supply it constantly, and you go on doing this, get new supply rate, you will get new storage. So, that is what you can do, and to find out the optimal scenario. So, that is how it is, that is how you go about getting supply and storage.